So, recording is started. So it's our great pleasure. Oh wait, we should probably admit people first. Okay. It's our great pleasure to have Debbie Leung here today. And I don't know if you guys know her, but she's really a pioneer of quantum information science. I think there's no other way of putting this. So many of the things we know and love, she did. She's currently a university research chair at the Institute for Quantum Computing at the University of Waterloo. And basically her expertise include anything quantum information, including quantum cryptography, quantum communication, measurement-based quantum computation, fault-tolerant quantum computation, and error correction. I think she got her bachelor's in math and physics from Caltech, got her PhD from Stanford, and then pretty much, I think, Caltech, and then became faculty where she is now. And without further ado, please go ahead.
Thanks very much for the kind introduction, and also for, most importantly, for the opportunity to share a result with you guys. I want to verify that the discussion, the formal presentation is 30 minutes. Is that correct?
Yes, and then we have some discussion. That's a rough. We're not very strict on it, but.
Okay, just to verify, because it's rather uncommon. Because of that, I have decided to pick a very unusual topic. It's a very isolated and very small, it's kind of self-contained, very small result that I hope to present and prove completely within 5 to 10 minutes in the talk. It is rather unusual, so I'll try my best to make it clear. Let me first acknowledge that this is joint work with Andrea Coladangelo, who is at the CS department at the University of Washington right now. When we were working together on this project, he was at Caltech and Berkeley. So I will, without delay, state the definitions involving the theorem that I'm going to prove. The definition will come with some examples to make them more natural and more intuitive. Then we will punch straight into the proof for the statement. I think I will have some time afterwards, and so I will explain the connection of the theorem that you see with what we call embezzlement. So the first thing I need to define is something very intuitive and really rather simple. You just want to define quantities on quantum systems. Mathematically, these quantities are functions on the density matrices, which represent the quantum state you have on the quantum system. So photon number is a quantity, spin, charge, and in case you have, say, a superposition of photon number, or is a mixture of state, then you can write down, say, an expectation over a number operator. So that's a quantity that we can associate as a photon number. I want to double check any question here.
Is this related to operators that are diagonal, or any operator?
Can you say that again?
Is that related to operators that are diagonal, or generally all operators?
Sorry, I should said that I have assumed that I have picked the Fock state as the basis in writing the number operator down, and yes, this is diagonal.
Okay.
So this is one example. I think it's a very physical example, photon number, spin, and charges. A more mathematical example of a quantity is the von Neumann entropy on a density matrix. It's mathematically just defined as you take the density matrix, it is square, it is Hermitian, posits have a definite trace one, you diagonalize it. Then you look at the eigenvalues. So the eigenvalues are lambda ones, they form a probability distribution. Then you calculate the Shannon entropy of that probability distribution. And then you get the von Neumann entropy. So it's a well-defined quantity on density matrices on any finite dimension. Okay? It's just one example of a quantity, which is a little less physical, but it is a well-defined quantity mathematically. Now, the third one I included for some other reason is a little longer. So it's called the entanglement of formation. So it is defined on systems that are composite. It has two parts, A and B. Then you have density matrices on AB. And the first thing you want to do is to look at all possible convex decomposition of rho into pure states. So I hope that the bracket notation should be familiar in this audience, and then we write the outer product. So after you write down any convex decomposition, so this side case need not be orthogonal. So there is actually a continuous unbounded number of these decomposition. After you write down a decomposition, you calculate the expected entanglement based on this decomposition. So to calculate the entanglement of psi k, you take the partial trace on one of the two systems. Say you trace out B, then you have a reduced state on A, you calculate the entropy. That will give you the entanglement for psi A. Then you take the weighted average over the convex decomposition. And it's called the entanglement of formation because it was first written down as a quantity that will allow you to prepare many copies of that mixed state out of EPR pairs. When you use a lot of EPR pairs and then you make many copies of that state rho. And that was written down as an estimate on how many EPR pairs you need. It's a minimization because it is a convex optimization, so you can attain the minimum. So there are three quantities that I have put down here, for example. Then once we have quantities, we have desirable properties of quantities. One of them is additivity. So it's simply defined like this. It's a bit informal, but suppose you have two states, C and omega. They can be different dimension. Suppose C is prepared in the first system, and then omega is prepared in the second system. The joint composite system is in the tensor product state C tensor omega. So there's no correlation between the two systems because it's a tensor product state. Then you want to evaluate the quantity on the joint tensor product state. If it always comes out to be the sum of evaluating the quantity on the first state in the first system, sum to the evaluation of the quantity of the second state in the second system, then you say that this quantity is additive. It's very natural for things like photons and spins and charges. It is also true for entropy. Now, entropy is in general sub-additive over two systems, but if you happen to have tensor product state, entropy is additive. So entropy is an additive quantity. But not all quantities are additive. For example, the entanglement formation was picked to share here because it's conjectured to be additive for 12 years before it's proved by Matt Hastings. In the joint optimization here, if you have two states, rho AB and sigma A prime B prime, then you need to write down this decomposition with pure state on AA prime versus BB prime, and then you jointly perform the minimization. And he proved that there exist two states whose entanglement of formation is strictly smaller than the sum of the two entanglement of formations. So any question on the concept of additive quantities versus non-additive quantities? Okay, pretty straightforward. The next property of a quantity that we want to consider is continuity. Of course, you want the quantity to change slowly. If you have similar state, you should have similar quantity. That's a very reasonable demand on something that quantify what you want to understand. Because we need to discuss what constitutes similarity for states. So we need to define a distance on the set of states. So we will use trace distance for this talk. If you have two states, mu and nu, they have the same dimension. Then the trace distance can be calculated by first taking the difference of the density matrices. Then you perform the eigen decomposition. Now the eigenvalue, some has plus signs, some has minus signs. You take the absolute value of each of the eigenvalues and then sum them up. This gives you the trace distance. Now the trace distance is very useful as a distance measure. First of all, it's zero if and only if the two states are actually equal. Then it is not increasing if you do not know which state has been given to you and you perform processing, you perform quantum, we call it TCP map on the unknown state. So you end up having to look at the distance between the process on mu versus the process on nu. And this distance is not increased by processing. It satisfies the triangle inequality and so on. So it has all the good properties. There is nothing fishy about this distance measure. Now, with the distance and the concept of continuity, we can see one example concerning the continuity of von Neumann entropy. The entropy, the difference of the entropy on mu and nu is always upper bounded by log the dimension of these states multiplied to the trace distance, plus another smaller term, I shouldn't call it smaller, which is given by the trace distance, log the trace distance with a minus sign in the front. This function decreases continuously to 0 if x decreases to 0. So it is, the function itself is continuous, but the slope is not. The slope is actually infinite at 0. So if you have a fixed dimension, but you talk about states that are increasingly close to one another, the second term is dominant. But if the distance is not extremely large and you have increasing dimension to consider, then the first term is dominant. Now, we often need to look at the first term. This inequality is used to show a lot of things. Like, for example, when you have channel capacity, you use the channel many, many times, then the dimension grow exponentially in the number of users. And so that this term will be the dominant term in that setting. And so, and because of the importance of, let's see. Again. Sorry, I lost the view to the room. It is a very strange notion of continuity. Without the second term, then we say that log d is the Lipschitz constant for the function. But it changes with the dimension. So the larger this dimension, the less continuous is this function, potentially. You do not know how continuous it is. But in the case with Fenner's inequality, it is tight. It is known that there are two states that will saturate this inequality. So there is nothing more you can do to make the general inequality better. Any question on this part?
Yeah, I have a question. I mean, since this is an inequality, I mean, the right-hand side is not continuous or as continuous as we want. It doesn't mean the left-hand side has the same continuous property.
That's right. If you have two states that you know for sure, then you can have tighter bounds. But without knowing what mu and nu are, this is the best you can put down as an upper bound. In fact, what I should say is that this log d is there because of the discontinuity of the slope of the eta function. That's where they come from. So it is a slightly awkward situation. It is continuous enough to give us a lot of results that we need. It is not continuous enough in other situation. Any further question on Fenner's inequality? Because that is the kind of prime example that we're going to consider.
Actually, I have a question to the trace distance. So if I were, if mu and nu were pure states, and I would just pick two adjacent eigenstates of a Hamiltonian in the middle of the spectrum, then I would assume that typically the trace distance is very small, right? Because
the trace distance is 2 in that case.
Yeah. Is that small?
Because you have
is that a
orthogonal
small
states.
number or a large number?
It's very large. 2 is very large.
But that's a bit unintuitive. So for example, I don't know if you're familiar with like the eigenstate thermalization hypothesis, for example. That's the thing that if you pick states from the middle of a spectrum of a Hamiltonian and you measure some observable of that state, then you get a very similar answer if you pick two neighboring states. So in that sense, it's continuous in energy. But you're telling me that if I take two eigenstates of the Hamiltonian, they're orthogonal, and the trace distance basically means they're far apart.
That's right. Because you can instead measure the energy, then you can tell which state you have. You can perfectly distinguish between those two states.
It depends on F, essentially.
That's right. In fact, the trace distance is related to operationally. I give you either mu or nu. I don't tell you what it is. You have to make a measurement and tell me whether it is mu or nu. Then your probability to get the answer right is half plus 1/4 of the trace distance. So when the trace distance is 2, you always know the answer, which state have been given to you. The two states are distinguishable, they're orthogonal. But sometimes they're really very indistinguishable, no matter how hard you try. It is kind of an unconditional information theoretic distinguishability that is captured there. So when the trace distance is very small, it is a strong statement that the joke is that not even God will be able to tell the difference. Because it's not allowed by quantum mechanics to know more. Then after, it's good to have this discussion here because this is what we're going to see. We're going to prove. If you have additive quantities, then your quantity is not going to be more than asymptotically continuous. So more precisely, consider any quantity with two properties. First, it cannot be constant. So there exists at least one dimension and two states of that dimension so that the quantity is different on the two states. This is condition one. The second condition is that it's additive for any two state that of any dimension. Now, if you have these two properties, then we say that it cannot be more than asymptotic continuous if for all rho sigma on any dimension, large D here, if you can write down a continuity statement like this, that the Lipschitz constant is log D to the power alpha, then alpha has to be at least 1. You can't have square root here, you can't have log D, it has to be at least 1. You can have log D to the power 2 or something, but it cannot be smaller than 1. So this is the statement. It essentially says that the kind of continuity that you're seeing, the kind of imperfect continuity you're seeing in von Neumann entropy is generic for, it has to be the case for all additive quantities. It is not because we lack the skill to prove it, it just cannot hold. Okay. It is a little unexpected that these two properties will be related, that it is additive versus whether it is continuous or not. So any question on what we're going to prove?
So do you know what would happen if it's sub-additive? I don't know if that's a meaningful question.
As a mathematician, I would say that my proof will not apply. So I do not know, there is no consequence from knowing that it is sub-additive that I'm aware of. Yeah.
Okay, thank you.
And the proof is really easy. And so I'll share that. So just removing the last portion so that I have a little more space on the slide. So I'm given 3 things. So in order to prove it, let me say that what we need to assume in order to prove the result. We need to assume that it's non-constant, is additive, and then we assume this continuity statement. We have 3 things together, and then we prove that alpha is at least 1. So that's the thing that we need to do. But for now, just look at the first two properties. The first thing is that the quantity also has to be invariant under permutation. In this case, just because the right-hand side of this equation is a scalar, I can swap f of c and f of omega. So so it means that my quantity has to be the same whether I look at c tensor omega or omega tensor c. Then the proof approach is to attempt to convert mu to nu, thereby changing the quantity in the system. One method to try to do this is to bring in an auxiliary state like this. Now, this auxiliary state has n copies of the system with small d dimension. And in the first R system, I prepare mu. And in the last n minus R system, I prepare nu. And then I have a formal mixture over all possible value of R from 1 to n minus 1. So this is the state that I would use to try to make the conversion. So to make the conversion, I bring in my state mu and tensor it with the catalyst, the approximate catalyst. I can give you a hint that this is going to work very catalytically. So I put the two states together. Then I try to arrange the system. I have n plus 1 system. I arrange them in a circle. My mu is here. Then the first R system is in the blue. The last n minus R system is in orange. And they arrange in a circle. Then the way to do the transformation is that I'm going to perform a cyclic permutation clockwise by one system. So the red one goes to the first blue one goes to the second blue one, and so on. And then the last orange one go to the red one in terms of, like, you should consider the system being stationary, and then you move the state clockwise. So then the state mu goes into here instead. And the state, this orange state nu goes to where the red state is. So we get the new state where the system is. And in the catalyst, or in the ancilla, I now have R plus 1 mu's and n minus R minus 1 mu's for the term that originally have R and n minus R of copies of the two types of states. Because I have taken one copy of mu out and pushed one copy of mu in the catalyst. Any question on this?
I think you were thinking about these states under the action of F, right? Otherwise, you wouldn't be able to bring that last nu to the very front.
So this is a swap this is a cyclic, this is a permutation operation, which is unitary. I'm permuting the state of system 1 to system 2, system 2 to system 3, and so on. And it's a unitary operation. And I think it's allowed by the axiom of quantum mechanics. Now, where on earth I find this state, I don't know. I did read a paper by Susskind about these states. Of course, these states are particularly chosen because they don't have they have some strange property. I'll discuss a little later. But if I can ask for a quantum state of my choice, and I have asked for this state, then this transformation is just a unitary operation. And so mu becomes nu, and my state here become a different state. For each term, R is replaced by R plus 1. Which is right. I haven't cheated. I have the same number of mu and nu's around. Every term becomes the next term in the sum. And so if you compare these two states, all but one term from each state will match up. So when I actually look at the difference between omega 1 and omega 2, I have two terms. I have one term which is 1 over n minus 1, and then it is a trace 1 operator afterwards. And then I have a negative minus 1 over n minus 1 with another state following it. So my trace distance here is never more than 2 over n minus 1. It is a straightforward thing to realize. So these two states are very similar if small n is very large. So that's observation 1, that I can perform this cyclic permutation. And it doesn't change my state very much if I can ask for a large number of systems there. I have a long mixture of different numbers of mu versus nu. For the physicists, you shouldn't be surprised. Because here, if you think about mu and nu as, if they carry different quantity of, if they carry different amount of a conserved quantity, I need to break the conservation law. And to break the conservation law, I have a large uncertainty in the state that I bring in. And roughly, this is where the possibility comes from. Okay. So this is one observation I can make, that I can turn mu to nu by using this catalyst. Then the second observation is that mu tensor omega 1 and nu tensor omega 2 has the same amount of the quantity because they are only differing by a cyclic permutation. I'm just relabeling the system. And then I use additivity to rewrite the first quantity as a sum of f of mu and f of omega 1. And then I use additivity to write the second quantity as f of nu plus f of omega 2. Then it is very simple arithmetic to realize that the difference of the quantity in the system that you're looking at between mu and nu is the same as the difference between the quantity on omega 1 and omega 2. It's just to say that the quantity is conserved by your cyclic property permutation. And since it's additive, the difference in the small system has to be coming from the difference in the big system. So they are both having the difference being the same constant we have in the first property here. I have taken the d and the mu and nu from property 1. And whatever that is, I just take it for use for the proof. So I have these two observations, and I'm just copying it once. And what happened with omega 1 and omega 2 is that you have the same constant change, but it's spread over a much bigger system. And now, remember that we have a third condition, that if I have a continuity statement like this, then I want to show that alpha is at least 1. Well, it's very easy now, because I just take rho to be omega 1 and sigma to be omega 2. My dimension large d is small d to the power n, because I have n system in the catalyst. And so I just plug everything in. The quantity, the difference between omega 1 and omega 2 is constant from observation 2. And then I just rewrite this a little bit so that n to the alpha is out in the front. D is a constant here. Small d is a constant. Then this is upper bounded by 2 over n minus 1. And this holds for all n. So there's only one possibility, is that alpha has to be at least 1. Because otherwise, if I make n larger and larger, I will get a contradiction. So, and this is the proof. Yeah, you rarely will see a proof on this kind of seminar, but this is small enough that I can prove it. So what you have seen is what we call embezzlement. You steal something from a large pool, and it is not very noticeable that you have done it. From omega 1 to omega 2, it's not very noticeable that I have done, because you can spread the change of the quantity over d to the n dimensions. So how much time do I still have in the end? It's already 5 o'clock.
Well, so we did 30 minutes, but maybe a little more. I mean, I'm on the edge of my seat, so I want to keep this.
Okay, so let me tell you I have presented things the opposite direction. We know embezzlement for much longer than this continuity and additivity connection. So let me tell you what is embezzlement. We all know what embezzlement in real life. It's a theft by the person who is entrusted with an asset. But the important thing is that it's not robbing. You don't want people to know. And it's not regular theft, because regular theft, if it happens, and people don't know who have done it, they still know that things has been stolen. So it's a different thing than robbery and theft. Embezzlement really is something that has to be well hidden so that no one knows. And that was first considered by these two embezzlers, Wim van Dam and Patrick Hayden, a long time ago. And so this is the formulation of the problem. You have a bipartite system or multipartite system later. And Alice and Bob start with uncorrelated state, 0 each. They are far apart, so they are divided by a wall. They can't do any quantum joint things together. They can do their own quantum operations, say, which means that isometries together with tracing. So just take it as isometry on the two sides. They can't turn 0, to an entangled state. Full stop. Because your entangled state have correlation, you can use it to you can find special correlation from this by measuring this state. So you can't start with nothing and then have correlation coming out of separate operations. It turns out that you still can't do it even with a catalyst. If they are allowed to ask for any catalyst of their choice on two finite dimensional system, and the task is to convert 0 to the state phi using the catalyst. But the catalyst has to be returned exactly. This is also impossible. In fact, it is really quite impossible in the sense that if this is a tensor product system, even infinite dimensional catalysts will not allow them to do this. If you use commuting observable system, then you can. That is work by my colleagues, Richard Cleave, Leung, and Vern Paulson several years ago. But they also show that if you have tensor product system, you can't do this, even with infinite dimension. The embezzlement of entanglement says almost the opposite, except you have the approximate here. You can embezzle any state psi to any accuracy by using the correct catalyst. That's the statement. There is a long mathematical statement that says that you fix epsilon, which is the accuracy of the embezzlement that you want to do. You fix the dimension of the state that you want to embezzle. You fix the state that you want to embezzle. Then I can give you the dimension of my catalyst and what is the catalyst, and also the transformation U and V that you need in order to perform this transformation. You act on AA prime separate from BB prime. You act on the catalyst time tensor with a 0. Then you epsilon approximate the state that you are not supposed to have. This is the statement that the embezzlement of entanglement can be done to any accuracy, while the exact thing is impossible. There's no contradiction here.
Is the secret that the state, the catalyst state is very large, has a very large dimension compared to the states that Bob and Alice have?
Yes, that's roughly where the situation is, yes. And in fact, we'll see some bounds.
Naive question, right? So what it looks like to me is that, so there's a no cloning theorem, right? So Alice and Bob can never kind of know what they're working with, but this embezzlement kind of lets you kind of clone a state, or is that completely orthogonal?
Oh, thanks for asking this. They know what they have to embezzle.
Okay.
Yeah, sorry about this. This is not an unknown quantum state. This is a known state that they want to embezzle.
Ah, okay.
And in fact, for the previous discussion, mu and nu is known to the parties. Except, yes, in that case, the cyclic permutation is independent of the state.
Okay.
But in this case, yes, it depends on the method we use is somewhat independent. So since you asked, I'll get into a little bit more detail here.
Okay.
So the result by Van Dam and Hayden is stronger than what I put here. you can have a family of catalysts that will work for any purple state psi. The only thing you need to keep asking that depends on psi is the dimension has to get bigger and bigger. But it is the same family of catalysts that will work for any state that you want to embezzle. And the identity, the description of the state that you want to embezzle will appear in the unitaries, because somehow something has to depend on that state, and it will be on the unitary. You will see a different method that has the unitary being basically independent of the state that you need to embezzle. And the dependence on the state goes to the catalyst.
Mhm.
And you already know how to do it. This is silly now that we have seen the first part of the talk. If you need to embezzle $1 from $1 million, you can't, because if someone tracked the amount of money, then you will be caught. But if the pool is a uniform distribution from $1 to $1 million, then you can embezzle $1, because the distribution is not very distinguishable from a uniform distribution from $0 to $999,999. And so this is the idea, how to do it. And the catalyst, as you can expect, is exactly what you saw earlier. We want to transform 0, 0 to phi. So you ask for n systems holding the bipartite state. So you have n A's and n B's, each isomorphic to the A prime and the B prime where the purple and the purple states live. Then you arrange them again in a circle out of the 0, 0s and n minus r's of the size. Now this time these are pure states, so you have a superposition, not a mixture, over the different values of r. You bring in bring in the 0, 0 on A prime, B prime, perform the cyclic permutation clockwise, and get phi out into A prime, B prime. You push the 0, 0 in, so you have one extra copy of 0, 0 for every term, and one fewer copy of psi for every term. Then the catalyst turn from psi to psi prime, which looks almost the same as before, except for a shift in the index R as before. It's the same idea. And so the catalysts have very high overlap with one another. This time, you don't even need to think about the trace distance. Just mentally take the overlap. And it has to be at least 1 minus 1 over n. And so the number of copies you need to achieve epsilon close embezzlement is 1 over epsilon copies. So it can be done. The original Van Damme-Hayden method takes about 1.5 column in the physical review format. It's not difficult either. But this one you can actually just show in the top. And so what's going on here? What's going on? Entanglement is a conserved quantity when you have local unitary only. So how do you get around with an approximate violation of the conserved quantity? You bring in a state that has a large uncertainty in the conserved quantity, which is entanglement here. And the other thing that is going on is that entanglement is, let's say, your catalyst. Suppose the initial idea is that this is an EPR pair. It's the kind of treasure that everyone wants. You're changing one E bit of entanglement. A prime, B prime has one E bit entanglement more, which has come from the catalyst A and B. So the catalyst A, B lose one E bit of entanglement. So how do you make it losing one E bit of entanglement without changing very much? The only thing that will make it happen is that the entanglement is not a very continuous quantity on AB. If it is continuous, you can't do it. You have to have a very large change in the state to lose one E bit, a constant E bit of entanglement. So it has a lot to do with the fact that entanglement is not very continuous. It is only just asymptotic continuous with the exponent alpha equal to 1, and no more continuous than that. In fact, because of fairness inequality, it is continuous enough that you can bound the performance of embezzlement using the continuity of entanglement. If you have big n dimension in the catalyst, then your error has to be at least quadratic in 1 over log n, because it is continuous enough to make it difficult for you to embezzle. I have maybe 1 or 2 more sentences to say after taking 10 minutes more than it should be. So why did Andrea and I look into the problem? We had a method to perform what we call the non-local game. We have this very small example with very these are basically Bell type violation that has very few measurement setting and very few measurement outcome. And we know that this game cannot, or the inequality cannot be maximally violated by finite amount of entanglement. The Bell inequality forces the different measurement to perform embezzlement, followed by measuring things that have been embezzled. So we use this setup to, you can think about it as a fixed, small experimental setup that you can test whether the 2 players actually have a large dimensional system that they have. They have a large dimensional entangled state because they are effectively forced to embezzle. And we want to push how, if they can't attain the maximum, but they're epsilon far from the maximum, how big the dimension has to be. We want to push that bound to be as large as possible. So after we got the result with entanglement, which at the time was exponentially better than the existing bound, we tried to make it better by looking for a more continuous quantity to embezzle. We thought that would give us better test for dimension. And the first thing is that we run into a contradiction because there is no such quantity. And that's how we got the result that you saw at the beginning of the talk, just to mention where that come from. I prepared the slides, but I think it's not appropriate to overtime by it's too long, so I will stop here.
That was a very nice talk. Do we have questions? Pleasure.
Yeah, thank you. This is very interesting. So I have a question about the first part when you show the alpha has to be bigger or equal to 1. In one step, I'm just wondering if you have assumed the kind of trace difference is given by that expression. You know it has a form of log d to the alpha power.
Right.
Or it could be some polynomial of d as a prefactorial.
Yes, if it is not as a polynomial of d, it is a lot worse already, right?
Yes,
log
right.
d is a lot smaller than a polynomial of d.
Right, but then you wouldn't be able to show, the alpha is 1, or you.
Well, I have a dimension. So the important thing is that I use log d just because it's convenient. But if I have a general function or a polynomial of d here, I could have substituted d over n there as well. It means that if I have a function, a polynomial of d up here, then I won't get any alpha bigger than 0. That's right.
Okay.
Yeah, but d is a very large number.
Yeah. Okay. So this is the log d. It's slower than any polynomial, so that's already some extreme case. And
that's right.
Okay.
That's right.
Yeah, I can get that. Okay.
We have more questions from the audience? Do we have questions from the online audience? If so, please just unmute yourself and ask. If I may ask a question, so basically the concept is that I have to have states with a large uncertainty, like in physics terms, I have to have states with a large uncertainty of a conserved quantity, right? So in physics, I'm thinking of some toggle state or something like this. Are there any constraints on how that uncertainty has to come about, or can it be a given state, say with the temperature and then some? Or can I make it more stricter than even if I knew how the uncertainty was kind of distributed?
Yes, quite a large number of different states will allow you to perform the transformation. Yes, you can use different embezzling states. It is yes, I should expand on that because this is how I first finally understood NMR. My PhD relies on NMR quantum computation. I know that there is a spin in the molecules, and I also thought that we wrote down something like, you have A0 plus B1, you can perform single qubit operation on your qubit. That's what I was told, working with Chuang. And at some point, there was the question, like, how can we change, if this a spin is conserved, how do you change it? Well, it changed it. It changed because you shine a probe. You use an NMR probe to shine some photon beam to the sample. And so there is some interaction between the spin and the photon. And so the spin has been taken away from the photon and deposited in the NMR system. Now the beam get out of the sample. And if someone take that beam, and if I see that some photons disappear compared to before the interaction, I would decohere between the 0 and the 1 state in my qubit. So the only way it can happen is that I cannot distinguish the beam with an extra photon or with one fewer photon, because otherwise I decohere my system. So similarly, I was told that the coherent state has the same form. There are different ways you can modulate the coefficients. The Van Dam-Hayden embezzler is universal in a way that it has a specific form for that one, because you want that state to be universally usable for any state that you want to embezzle. Then it tightly constrains the form of it. The rest of this, you don't need to, because you know what you need to embezzle out of.
Do you have more questions? All right, if not, then let's thank our speaker again.